So, we discussed this scattering theory yesterday, and it looks like that from the feedback I got from my students, it looks like another explanation and probably a thorough explanation of the scattering is required, particularly with the view that there are people from pharma industry and possibly even teachers who are trying to go through this course. And so, what I thought was I will prepare some slides, reorganize them and then go through it once more, so that we get a clear feel for the scattering theory, because this is the basis of all scattering, and eventually the diffraction and what happens when X-rays fall on a crystal, and how the diffraction appears, and how the equivalent points respond, and how the atoms and molecules respond, and so on. So, what we therefore say is that when electromagnetic radiation passes through a crystal, the electrons are perturbed by the rapidly oscillating electric field. So, here is a wave. The wave, as we know, can be characterized in terms of its amplitude, and this angle at which it starts is referred to as the phase angle. The wavelength associated with the wave is now given by lambda, and that is the distance from the crest to the next crest. It is also equal to the distance between the trough and the trough. And therefore, when this electromagnetic radiation comes in and falls on an atom, this is a bloated picture of an atom. I have taken helium as an example. So, what happens is that there is a central nucleus which is positively charged, and then there are electrons, there are two in the case of helium, and these electrons carry a negative charge. So, when this wave comes and disturbs this atom, as we see here that it generates a rapidly oscillating electric field, and this because the fact that the wave which is coming in can be described in terms of an electric field, which is E naught cosine 2 pi nu t, taking only the real part, or E naught e to the power of I to 2 pi I nu t, which is taking into account the complex nature of a wave. So, these electromagnetic waves in general are complex quantities. So, to describe this wave, we make use of the complex numbers. We will go into the detail a little later, but at this moment there is an incoming wave which comes and hits the atom, and the atom is said to vibrate. Now, because there is a heavy central nucleus, the electrons are disturbed much more, the outer electrons particularly, and as a consequence the positive and the negative charges develop, and therefore it becomes a dipole. A positive and a negative is separated by a distance is a dipole. So, this dipole now oscillates with the same frequency as the incoming radiation. So, there is no change in the frequency, and so we call it as coherent radiation. And according to electromagnetic theory, any oscillating field of this kind will generate its own wave, as is shown here. So, this wave now comes out in this form, and this particular wave now is from this particular atom. So, it may so happen that there are several atoms in the crystal, and all these atoms are connected to each other and so on. As a consequence, we will get a large number of waves coming out with this interaction. The advantage again is the crystal and the symmetry, and that is why we keep on stressing on the symmetry throughout this course. The fact that these atoms are inside a unit cell, and the unit cell obeys the laws of symmetry. The issue of the obeying of the laws of symmetry brings in the fact that these atoms now are inside a lattice, and since they are inside a lattice, the presence of the atoms follow the symmetry rules, and since they follow the symmetry rules, the coming out of these waves are actually in a direction which is decided not just by the presence of the atom inside, but also by the presence of where the atom is present. Depending on where the atom is present, different kinds of waves get to be coming out of the system, and therefore we have several atoms giving rise to their own waves. And so, if you see this as the equivalent of a crystal at this particular point, we see that there is a source which sends electromagnetic radiation as spherical waves. Sufficiently long distances, these spherical waves can be approximated to a plane wave, and this now in turn will generate its own spherical waves. So, this point now becomes, if this is the crystal, now crystal becomes the source. So, from this we get lots of waves coming out, and therefore, we have the process of interference which we recorded yesterday, and which tells us that only in certain directions we will have the bright light coming out, and the rest of the directions will be dark. So, we get in a 3-dimensional geometry, we get spots, dark and white spots, and these spots now will go to the receiver, which is essentially a detector, and we find out as a consequence the nature of the way in which these what we call as eventually reflections come up. We will get to a better understanding of it as we go along. See, the electric field that is associated with the disturbance which occurs due to the presence of the wave coming in, the incoming radiation, this is a wave, and that particular wave now introduces a certain disturbance at every atom position. So, wherever there is an atom, these dipoles get developed, and then we get these oscillations, and these oscillations will in turn generate waves. So, if we consider the electric field as E naught cosine 2 pi nu t, this quantity E naught is the amplitude of the wave, and cosine nu t now represents the so called phase associated with the wave. So, the entire wave is described in terms of the amplitude and the phase that is associated with the wave. And this particular electric field now spreads as a wave front, and that wave front goes with the velocity of light. The c is the velocity of light, because X-rays are photons and they also have the velocity of light, they are essentially light. So, these photons therefore will move with a velocity of light. Now, just as we were mentioning, as the spherical wave fronts which spread from a given point at very large distances at a particular time t, what really happens is that this phase associated with that wave is at a time t at a distance r. So, we now move to a distance r from the position of the scatterer, and at time t, if we observe the behavior of the wave which is coming at a distance of r, it is actually the phase that is emitted from the source at a time t minus r by c, because it is travelling at a velocity of c, r is the distance at which we catch it, and therefore, whatever we measure at t is now that which originated at t minus r by c, and that is the phase which we get at t minus r by c, and therefore, the phase will be 2 pi nu times t minus r by c, or 2 pi nu t minus r divided by lambda, where lambda is c by nu. This is something which there was a mistake yesterday while writing down, even though I explained it as lambda equals c by nu, there was a mistake. So, lambda is defined as the velocity of light divided by the frequency. We have also noted that the frequency will not change after scattering, that is the coherent scattering. Now, what we do is we consider a situation where the r, distance r is now becomes r plus delta r. So, if delta r is an additional distance, that means there is an increase in the path length. Whenever there is an increase in the path length, there is a corresponding decrease in the phase. So, as we go longer and longer distances, the phases keep on reducing associated with the scattering vector, and therefore, we see that it leads to a decrease in the phase, and that decrease is 2 pi delta lambda. So, r plus delta r becomes now 2 pi delta lambda will be the decrease in the phase, and since we already said that these are electromagnetic waves, the electromagnetic waves are indeed expressed as complex numbers. So, instead of E naught cosine 2 pi nu t, we have E naught exponential 2 pi I nu t. So, this now is the representation which is in the organ diagram below. We have the imaginary axis and we have the real axis, and suppose we take two such waves coming out from this experiment. We have discussed only one here. Suppose there are two such amplitudes which come out from a single point taken as the origin. Then we have a E1 which has a phase of delta 1, and then we have an E2 which has a phase of delta 2. Then what happens is that when these two combine due to interference, we will have the resultant, and the resultant is E, and the corresponding value associated with the phase is delta. So, we notice that as we go to higher and higher distances, so if r becomes r plus delta r, there is a decrease in the phase by 2 pi delta nu. So, what are the consequences of these? So, we have to now see that there is a wave. The wave is represented by a complex equation which is E naught exponential 2 pi I nu t. This particular quantity represents the wave. The first part, which is E naught, is the amplitude of the wave. Exponential 2 pi I nu t is the phase associated with the wave. To describe the wave fully, we need both these quantities, the amplitude as well as the phase. Now, what really happens is the amplitude is the one which carries the amount of energy in the system. So, if we consider E naught square, which actually represents the total energy, it is also referred to as the intensity of the wave. So, when the intensity of the wave has to be looked at, we consider the E naught square as the intensity of the wave. So, the amplitude square. So, what happens in a typical experiment which we did in the last class about the interference experiment, for example, is the fact that when waves come in and two waves interact with each other, there is an interference, and that interference depends upon where the waves originated from. That means it depends upon the delta 1 and the delta 2 which are shown here. Depending on the value of delta 1 and delta 2, we will get a resultant which is corresponding to the phase delta and the value E. So, what is happening in this situation is that there are two waves coming out and these two interfere, and the interference results in an addition of these two waves which are coming in. The addition is with respect to the vector directions E1 and E2. So, what is the consequence of this? The consequence of this can be seen in the next slide, where we see that we have the complex wave coming in. So, the incident wave which is coming in, this is a wave as we have imagined before. So, it has an amplitude and a phase. Now, this incident wave which is representing the energy associated with the incoming radiation, which is E naught square is the energy. So, that is referred to as the intensity. So, there is a certain intensity of the wave, that is how the light intensity comes up, and that intensity is now incident on let us say a small volume d of r in matter. It could be a crystal, it could be any other state of matter, but we will consider a crystal. So, inside the crystal there is a small elemental volume d of r which we consider, where it has rho of r d of r as the electron density. That means there is a certain amount of electron density which stays inside this little piece, and because this electron density is there, when the incident radiation falls on that, it undergoes a scattering because of the presence of the electron. As we discussed earlier, there is an atom is attached to the electrons, and the electrons are the ones which interact with the X-rays. Please notice that whatever interactions that occur in an X-ray diffraction experiments are more or less, or we can say almost entirely, due to the interaction of X-rays with electrons. This is a point which we should never forget, and therefore, depending upon the electron density, we will get the scattering variations, and that will eventually interfere and generate the scattering. So, the incident radiation which is coming in, which is generated from an X-ray source, can be taken as in terms of a unit vector S naught. S naught is referred to as the unit vector, and this unit vector S naught now represents the incoming radiation, and this, if we sit at an origin O 0 0 0 here, we decide that this is the origin, and we look at what happens when this electron density presents itself in front of the incident beam. So, in the incident beam comes up here and falls on this rho of r d of r, and then it scatters in this direction p p prime. So, this direction in which it scatters can also be considered in terms of a unit vector S. So, S naught is the incident unit vector and S is the scattered unit vector. So, if you consider now the two paths, the path traversed by this line and the path traversed by that line, you see that there is a difference in the path length. The path length is in terms of, so what we do is to take this origin, drop a perpendicular to this point, which is now representing the incident radiation, and take this point, and from the electron density which is present at DFR, we drop a perpendicular. So, that is r dot s and this is r dot s naught. So, the path difference therefore will be r dot s naught minus s. That is the additional distance which this wave, this line has travelled representing the wave compared to this particular line. Since there is no electron density here and there is electron density there, the extra distance that is travelled is the path difference. We already saw that a path difference of delta will introduce a if it is positive, it will introduce a negative change in the path in the phase difference. So, we can always calculate the phase difference in this particular case. So, the path difference is r dot s minus s naught. So, the phase difference will be 2 pi times s minus s naught divided by lambda, where lambda is the wavelength. So, the phase difference for the path difference of r dot s naught minus s, the phase difference is 2 pi s minus s naught divided by lambda. So, when we now decide to represent what is the amplitude associated with this electron density rho of r d of r, we bring in the issue of E naught. That E naught is rho of r d of r as given here, and this now becomes the so called phase term. So, the phase term you see is now saying s minus s naught by lambda, which is now the path difference 2 pi times s minus s naught by lambda. Since this is a complex quantity and it is with respect to r dot s minus s naught by lambda. So, this is r dot s naught minus s, the path difference. So, the phase difference should be the phase difference will be smaller. So, larger the path difference, larger is the phase difference, and therefore, there is a change of sign. The change of sign is incorporated by changing s and s naught positions. So, we have therefore, the complex amplitude expressed in this following way. So, rho of the r d of r, rho of r dr, this part will explain the will consist of giving the E naught part, the amplitude part, and this is the phase that is associated with the wave. So, therefore, we can now express the complex amplitude associated with the wave in terms of rho of r d of r exponential 2 pi I r dot s minus s naught by lambda is the phase difference. Now, we make an approximation here. It is not an approximation, we give a nomenclature for this quantity s minus s naught by lambda. Notice that s minus s naught by lambda is representing a distance which is in inverse space or reciprocal space, because lambda is the wavelength and it is measured as a distance. The difference s minus s naught is also a distance. So, therefore, we now replace s minus s naught by a value capital of R, and this capital of R is referred to as the scattering vector, and this scattering vector will be equal to s minus s naught by lambda. So, therefore, this quantity R has dimensions of reciprocal length. Remember this, because we are now going to worry about what are the types of possibilities this vector R can take in a situation where we have the scattering occurring inside a crystal. So, this vector R and its properties are what we will worry about as we go along. So, to summarize this part of the discussion, we have an incident radiation and then a scattered radiation. It falls on a certain electron density rho of r d of r, which is a small elemental volume inside the crystal, let us say. So, as a consequence, we get a path difference associated with the path in which the wave traverses, and that is r dot s naught minus s, which leads to a phase difference which is minus of r dot s naught minus s, which is s minus s naught, r dot s minus s naught divided by lambda multiplied by 2 pi, I indicating that this is a complex quantity. So, we therefore get the expression for the complex amplitude as rho of r exponential this, and we now define s minus s naught by lambda in terms of a vector r, and this particular vector r therefore has dimensions of reciprocal length. So, what you notice in this expression is very interesting. There are two vectors, a little r and a big R. The little r is referred to the direct space distance the distance from the origin to the electron density. So, this is in direct space, and the capital R is in the reciprocal space, and therefore, R dot R now is a product which represents a product of a distance and a quantity which has the dimensions of reciprocal distance or inverse distance. And so, R dot R will turn out to be a simple number. We will show that later on, but in this particular case you see that, as I have written here the caption to the figure, the path P prime is R dot S naught minus S longer than the path P, and therefore, the corresponding to a decrease in the phase, which is 2 pi R dot S minus S naught by lambda, and we take this as a complex quantity. So, I gets in up there. Now, if rho of R is a continuous electron density, suppose we have a little element of volume considered and we said it is rho of R d of R, but it is there now in the entire crystal. So, rho of R now represents the continuous electron density distribution, then the amplitude will be an integration over this quantity. So, this complex amplitude which we are talking about, the complex amplitude associated with the wave now coming out from a crystal which has a continuous electron density distribution. So, we assume that inside the crystal we have all these atoms and molecules and so on, and the electron density that is associated with all these atoms, molecules and so on are distributed in such a way that there is a continuous electron density distribution. This is an assumption we are going to make. So, the whole entire crystal is now filled with electron density. Of course, the electron density will be more when there is an atom position, much more when there is a bigger atom, very less when there is a smaller atom, and between molecules and there is some space in which the electron density will be reduced considerably. But essentially the whole unit cell now is filled with electron density. If that is the case, then the complex amplitude for the entire crystal will turn out to be f of r integration over rho of r exponential 2 pi I r dot r d of r. So, this is an expression which we call as the structure factor. I have not written it down here because we are going to bring it again and again throughout our discussion, but please note that f of r is referred to as the structure factor. That is because it represents the strength that is associated with the amplitude of the structure. So, because of the fact that there is electron density rho of r d of r inside the crystal, this quantity f of r gains strength. Now, we define what we call as a Fourier transform. We will define at this moment, and we will see that the Fourier transform is essentially a value of rho of r taken outside now. So, that means f of r can be converted to rho of r by this expression, and rho of r can be converted to f of r, or f of r can be converted to rho of r by this expression. Rho of r can be converted to f of r by this expression, and these two together form what are known as Fourier transforms of each other. We will be spending considerable amount of time in understanding this quantity, but essentially what we say here, what we see here is that rho of r is in the real space, that is the electron density. So, if we want to calculate electron density, we need to have the f of r values, and these f of r values are in what we call as the reciprocal space. So, the r vector is in reciprocal space, the capital R vector, and the little r vector is in the direct space. So, we also see that there is a change of sign here, exponential minus 2 pi I r dot r d of r, that is the representation of the electron density. So, given the value of f of r, in principle we should be able to get rho of r, provided we know about this quantity which is the phase. On the other hand, if we are given the f of r and the phase value, it should be possible to get rho of r. It is also indicative that if we know rho of r, the electron density distribution, where the atoms are sitting and so on, we can easily calculate the quantity f of r exponential this, the whole thing can be calculated. So, if we know the structure, we can get the structure factor. If we know the structure factor, in principle we should be able to get the electron density. The only catch here is that we need to find the phase. The problem is referred to as the phase problem, because the finding of the phase is not going to be straightforward, because the waves which are scattered emanate from different points in the entire crystal, and we do not know from where it is coming from. It also depends upon where the atoms are sitting. Even though we now can imagine the crystal to be consisting of several planes, and then we can actually look at the possibility of sending an X-ray beam onto a given plane and trying to get the intensity out of that plane. The actual scattering is done by the electrons and therefore the atom positions. So, whenever we refer to as x, y, z and say there is an atom in that particular position or an object in that position, it is the object which scatters. It is not the plane inside the crystal which scatters. But we will see as we go along, because this is something which will always be confusing when people talk about the scattering coming from planes. So, we have to sort out what is the relationship between the scattering that comes from the planes and what is the relationship between that and the electron density that is associated with the entire unit cell. So, the entire unit cell has atoms and molecules and so on, and it is these electron density associated with these atoms and molecules which cause this scattering. You have to have a physical presence of the electron density to scatter this wave, but it is not necessary that this electron density should be associated inside the crystal with a plane, because we have been deriving equivalent points in the earlier classes, and the equivalent points clearly tell us that the objects are generated by symmetry operations. And these objects which are generated by symmetry operations either are associated with general positions or they are associated with special positions. The general positions and the special positions we have refer to the possibility of having atoms associated with planes. It is not telling us or planes or axes or whatever. So, if there is an atom sitting on a two-fold axis, we get a special position. Atom sitting on a mirror plane, we get a special position. This analysis we have done in the last classes, but we have not done an analysis where the atom has been restricted to sit on a given particular plane, and that particular plane need not be having a mirror symmetry. But what we are going to do as a measurement of the scattered radiation, because of the fact that the scattering now is in very loose terms quantized with respect to the crystal, because the measurements will come now with respect to where the scattering material is located, and this is located by symmetry rules. So, the laws of interference will tell us that where these spots will come. So, it is not a continuous distribution of intensities, we get discrete distribution of intensities. So, this is where we have to get a very clear understanding, and we will make an effort to get a clear understanding of this aspect as in the future classes and in this class onwards. But what is very important is these two equations. These two equations now are the key equations in structure determination. So, either we get to measure FFR. We know that we can measure FFR from whatever discussion we have had now, because we can measure the intensity of the spot which is coming out after the diffraction, after the scattering. And scattering is now giving a spot because of the interference rules which we have put in on a three-dimensional object. So, the scattering is now coming onto that particular spot. So, we can measure the intensity of this spot. The square root of the intensity will give FFR, but it gives only the modulus of FFR. So, we need to get the phases. So, we need to get the phases in, and we will put these phases in. Once we evaluate the phases, we should be able to get to the electron density, and that is the way in which we approach. Of course, the other approach is to have the electron density already known. We know where the atoms are and so on. We can calculate the corresponding FFR. Now, you see the advantage here. The advantage here is the following. See, since we have a problem of determining the phases experimentally, we cannot assure the accuracy associated with the phases. Because of the fact that we cannot assure the accuracy of the phases associated, the first calculation of using FFR estimated phases to give a rho of r will be very approximate. So, we may not have the correct electron density. We may have a nearly correct electron density, but not the perfect electron density. So, what we have to therefore do is use these two equations alternately. So, when we use these two equations alternately, so once we have this information of approximate FFR corresponding to the actual FFR, this approximate FFR now is fitted into this equation. The FFR, the modulus of FFR is accurately measured by experiment. The approximation comes only in the phase. So, once we lock into these phases, we can go back and calculate the electron density. So, the way in which we process this protocol is known as refinement. So, we go back and forth, and as we see go back and forth, we can get more and more accuracies associated with the rho of R calculated, and therefore, the rho of R, the f of R which is calculated from the rho of R, which is now going to be the calculated rho of R, will be very nearly the correct structure, and we keep on repeating until the rho of R which is measured and the rho of R which is calculated eventually go towards 0. They may not go exactly to 0, but they go towards 0, and then we say we have determined the structure accurately. So, therefore, please remember that these two equations, which are Fourier transforms of each other, are actually lifelines during the structure determination protocol. So, we must have an idea of how to use these, and everything originates from the fact that we have the scattering coming from the electron density that is associated with the material, in this particular case with the crystal. So, if there is large number of atoms inside the crystals, that is one way in which the scattering can come. Of course, it automatically increases the volume, because each atom will occupy approximately 18 angstrom cube volume in a general calculation. So, if you have that kind of a volume, if you depending upon the size of the molecule and the size in which it has to grow into the unit cell, the unit cell size changes. So, if you have a single atom, that single atom now will essentially occupy 18 angstrom cube volume, that is the space it generally occupies. So, here the assumption is that atoms are spherical, number 1, and they remain spherical even inside the crystal, even after they become parts of the molecule, and these molecules now go in and sit in the unit cell. Under these circumstances, therefore, we have to be we are making a very serious approximation, because we are neglecting the chemistry of the whole situation. The atoms are not going to be spherical in a molecule situation, because they get deformed, but we are now telling that the deformation is so small. As a first approximation, we can still use these two equations to get to the final structure with respect to that. Okay. At this time, we can stop.